So it says after the collision, the total momentum of the balls in the x direction is rho x, and the total momentum in the y direction is rho y. Which is correct for rho x and rho y? So we want to work out after collision. So we look at this scenario here. So let's do it in the x direction then. So we've got rho x. So that looks like mass times velocity of p. So the mass of p is m. The velocity of p afterwards is going to be v1, but it's the horizontal component from 30. If it goes through the angle, we use cos. So that's cos 30 plus the momentum of q. We have q, which has a mass of 2m, and the velocity is going to be v2, and again it's the horizontal component through the angle of 20, so that's going to be cos again, and that's cos of 20. So the only line that shows that clearly is A and C. Okay, let's do the total momentum in the y direction then. The total momentum in the y direction after collision is m1, which is mass of 1, times the velocity, which is in the vertical direction now. And that looks like it's sine, because it's against the angle, so that'll be sine 30. And we're going to minus it because v2 goes the opposite way. So v2 obviously goes opposite to p, so that's going to be minus m2 v2, well, m had a mass of 2m, so it'll be 2m v2 sine 20. Now we don't really have a scenario that shows this clearly. Let's look at C, for example. It says 2m v2 sine 30. We have sine 20, so that looks a bit different. And we've got m v1 sine 20, and we've got sine 30. So that looks different. And D, they have the cos terms, and we know vertically it can never be cos. So now we're stuck. We have A or C. So let's see. The momentum in the y direction after collision must be equal to 0, because the momentum before had no y component, and therefore the momentum before was 0. If I did 2m v2 sine 20 equal to m v1 sine 30, that should be equal to each other. So we know the total momentum in the y direction after collision is equal to 0. A looks like the best answer there. I've got another question here. We're going to work out the ratio of v1 over v2. Now I can do the momentum in the x direction and the y directions and see which is the best to use. So let's do the x direction then. In the x direction, I just have simply m1 v1 of x. So that looks like m1, well, it's going to be called u if it's before the collision. So u times, well, there's no angle. This is just going to be m1 v1 plus m2 u2. But we know the stationary particle was for y, and y doesn't have velocity, and therefore that component is just going to be 0. I should say that m2 is actually 4 times the mass of m, because it says it there, and that should be equal to the momentum after collision. So that looks like m1, this time will be the x component to the 60 degrees. If it goes through the angle, it's cos, so that's m1 v1 cos 60 plus m2, which is 4m v2 cos, well, if it's 90 degrees to v1 and v2 and 60 degrees is above, that'll be 30 degrees below, so that'll be cos 30. We've got too many unknowns to solve for anything here, and therefore I'm going to try and do the momentum in the y direction. So let's see if that helps me there. Before the collision, we know there's no y component, so the momentum before is 0, and that should be equal to the momentum after collision. So afterwards, we'll do the y directions now, and we can see they're both opposite, so they're going to be minus from each other. So let's do m1 v1 sine of 60 minus m2 v2 sine of 30. Let's put some numbers in then. So we've got m1 v1. We know sine of 60 is simply root 3 over 2. And we know sine of 30 is just a half. We'll take 4m v2 a half to the other side. So we've got 4m v2 times a half equals to m1 v1 root 3 over 2. Let's get the ratio of v1 over v2 that the question asks. So we'll have, let's do it here, v1 over v2 should be equal to 4m a half divided by m1 root 3 over 2. Do a bit of maths, the halves cancel out here, and the m's cancel out there, and we just get 4 over root 3. And that looks approximately similar to 2.31. The answer is A.